Welcome to the lecture on forced vibration of single degree of freedom system. Today we will discuss the magnification factor and frequency response curves. So we were discussing about the single degree of freedom system under harmonic excitations, and we found that there are the complete solution is of the two parts, the transient part and the steady state part. The transient part decays with time, and the steady state part is remains. So here we will study some characteristics of the steady state part. So we write the equation. So we have the equation. So this was our system, spring mass damper system subjected to some force F0 sine omega t. And here we found that the xp, that is the steady state part, that is x sine omega t minus phi, and here x was given as f0 upon k minus m omega square. So this was x, and we had the phi, that is tan phi, that was equal to c omega upon k minus m omega square. So we can rearrange these terms. So we can have f0 by k. So we take k outside of this under root. So we have 1 minus m omega square, okay, by k. So we are taking k outside here. We have c omega by k here, and this k will go on in the numerator. Now we can write here c omega by k equal to c by cc into cc into omega by k. So we multiply and divide by cc. Cc is the critical damping, as we have already defined this term. So we can write here c by cc into cc is 2 root k into m into omega by k. So c by cc is nothing but damping factor zeta, and here 2, so 2, let's take 2 here, and here k will be like omega and root k, so here root m by k, so it is omega n equal to root k by m, so it will be like this. Similarly, this term m omega square by k can be written as omega square by k by m, and k by m is nothing but omega n square. So we can write here omega square by omega n square. So here x, we can write x equal to f0 by k upon 1 minus omega square by omega n square whole square plus c omega by k is 2 zeta omega by omega n. So 2 zeta omega by omega n whole square and under root. Okay. Now what is f0 by k? So this is xst, we defined xst, that is the static deflection under some constant force F, under some constant force F0. So if we apply some constant force F0, the system will deflect with this amount, so that's why it is called static deflection or zero frequency deflection. So we can write and omega by omega n, let's define as the frequency ratio equal to R. So we can write this equation x equal to xst by 1 minus r square whole square plus 2 zeta r whole square under root, or x by xst or here we can write x by xst equal to 1 by 1 minus r square whole square plus 2 zeta r whole square under root. So this quantity x by xst is nothing but it is called the magnification factor. So this is called equal to m magnification factor, mf. Let's say it is mf, we represent it as mf. So this is equal to mf. Okay. Now what about this phase? So tan phi equal to c omega by k upon 1 minus m omega square by k. So here we can write equal to, so c omega by k is 2 zeta omega by omega n upon 1 minus m omega square by k is omega square by omega n square. So omega square by omega n square. So this is equal to 2 zeta r upon 1 minus r square. So phi equal to tan inverse 2 zeta r upon 1 minus r square. So this is the phase angle of this equation. So this the response of the system, that is x equal to xp equal to x sin omega t minus phi. So it is the steady state response. And what is this x? X is the amplitude of the steady state response, and xst is the zero frequency deflection or static deflection under some constant force f0. So this is magnification factor is the ratio of the steady state amplitude of the steady state response upon the zero frequency deflection. So this magnification factor is a function of r and zeta. So zeta is damping factor and r is the frequency ratio. It means that for any given damping, if we change the r, means we change the ratio of the force frequency upon the natural frequency of the system, we will get a curve, okay, for different r for one damping factor. Similarly, if we take several damping factors, we will get a group of similar curves. So these curves, because they tells, so for example, if we take here like x by x st and here r, that is omega, and for some damping we are getting some curve, then for other damping we are getting some curve. So we are getting this r is nothing but omega by omega n, so frequency ratio. So this curve tells us the response, steady state response amplitude at some force frequency, some forcing frequency. So that's why these kind of curves are called the frequency response curve. So here frequency response curve we can plot for a single degree of freedom system. Okay, so r equal to omega by omega n, and here it is mf or x by x st. So this is in this curve. So we can plot this frequency. So this is the frequency response curve that we are going to plot, frequency response curves, because they are for certain frequencies. So, so we can plot this. So here we have so this is zeta equal to 2, 1, 0.7, 0.7, 0.5, 0.25, 0.1125, and then zeta equal to 0. This is zeta equal to 0. So this is the frequency response curve. Now this curve tells some important characteristics, and it helps us to design a system that of our choice based on the limits of the vibration response or the amplitude of the vibration. Because here we can select our interest of frequency range, that in which my system is subjected to some force. So we have some frequency range, and in that frequency range what response we are expecting, we can select the damping value so that our system response is staying in our choice. So this frequency response curve, we are seeing that, please note this curve. We can see that if we are increasing the damping, the response of the system is decreasing, means the amplitude x, steady state amplitude x is decreasing if you increase the value of damping zeta. and that is obvious because we damping is the uh, parameter that controls the vibration response. Moreover, we can see that when we are near the r equal to 1 or omega by omega n equal to 1, or our forcing frequency is equal to the natural frequency of the system, then the response is very high. Response is very high. Although if we increase the damping, the response is decreasing, but in compared to the other regions, for example r less than 1 or r much greater than 1, the response is quite high. When r equal to 0, the response is x by x st equal to 1, means x equal to x st. So that is the definition of the zero frequency deflection. So when r equal to 0 means we have some force F0, a constant force is acting, so that the response is equal to x st, and that's why x by x st equal to 1. So all the curves are starting at x by x xt equal to 1, and they are moreover we can see that there are some peaks occurring. We can see some peaks. Here are this peak 0.5, some 0.25, 0.25, and so we see that the response is not taking place maximum at r equal to 1, means at resonance the maximum is not taking place, but maxima is taking place little earlier than the resonance point. Okay, and we see that when we are decreasing damping, we are more going close to the peak is more moving towards the resonance condition, that is r equal to 1. If we have the 0 damping, so zeta equal to 0, I mean no damping, the response is infinitely large. Okay. So now we want to know that what is the peak frequency, or at what value of r the peak of these curves occur. So if we want to get the peak, we can get it by differentiating this equation with respect to r and equating to 0. So dmf by dr equal to 0, then we can get the maximas. So we have this implies that d by dr, and this quantity we can write 1 minus r square whole square plus 2 zeta r whole square. And this is minus half. Okay, so this equal to 0. So now we differentiate it, and let us say this quantity is like we say r, so minus half into r minus 3 by 2. Okay, so this is r power minus half, so minus half r minus half minus 1, so minus 3 by 2. Now we differentiate inside. So here we have 2 1 minus r square into minus 2r. So 2, so x power n, so n x n minus 1. So 2 1 minus r square into inside, so 0 minus 2r plus this quantity. So this is 4 zeta square, this is 4 zeta square into r square. So r square is again 2r, okay, and this is equal to 0. Okay, so let's take this term mainly. So here we have we can take 2r outside. So we have in fact we can take 4r. So if we take 4r and so it is minus 1 minus r square and plus 2 zeta square equal to 0. So here r equal to 0 where we get this unity, or we make this equal to 0. So minus 1 plus r square plus 2 zeta square equal to 0, minus 1 plus r square plus 2 zeta square. So it means r square equal to 1 minus 2 zeta square, and so r equal to under root 1 minus 2 zeta square, and so omega p by omega n equal to root 1 minus 2 zeta square. This implies omega p equal to omega n root 1 minus 2 zeta square. So what we are getting that our maxima is occurring at r equal to root 1 minus 2 zeta square, and to occur a maxima this quantity should not be negative. It means 1 minus 2 zeta square is greater than 0. So it means that so we take the case of positive quantity. So here zeta is less than 1 by root 2 or 0.707. So if we have the value of damping so we will get the peak only if our damping is less than 0.707, and this we can see from the curve. We see that when this is the dotted line is the 0.707. Here we are getting the peak at unity, but after this we are increasing the damping because it is 1 2, we are not getting any peak. So and for zeta less than 0.707, so it is 0.5 0.25, we are getting clearly the peaks. So a peak will only occur if zeta is less than 0.707. Then what will be the value of magnification factor when r at the peak? So what is the value of magnification factor for the peak? So we can put this in the equation here. So we will get mf equal to 1 by under root. So 1 minus r square is we can write here. So it is 1 minus r square here. From here we can write 1 minus r square equal to 2 zeta square. So here we can write 2 zeta square whole square plus 2 zeta into r. So r here we get, so 2 zeta r square, so 2 zeta square into r square. R square is nothing but 1 minus 2 zeta square. So here we can solve it. So 2 zeta whole square we can take outside under root uh, 2 zeta whole square. So we can take 2 zeta outside here, and this is zeta. So zeta square plus 1 minus 2 zeta square, because here we can write 2 zeta into zeta. So 2 zeta whole square that comes, and here zeta square remains. So this we can write 1 by 2 zeta under root 1 minus zeta square. Okay, so this is MF at RP. So peak. So this is at. So here we can write that MF at R equal to RP. So peak equal to 1 by 2 zeta root 1 minus zeta square. So this is only function of damping here, and these peaks we can find. Okay, and we see that if we are decreasing the damping, okay, we are going as MF equal to 1 by 2 zeta. We are tending to 1 by 2 zeta. So we are going to tend towards this line. Okay. So here it is clear that we have why we have this 0.707 that clarifies the peaks and the peak response and absence of the peaks. And from here we can understand the effect of damping, because if we are increasing the, if we are near the resonance condition and we don't have the damping, the amplitude is infinite, but if we are increasing the damping, the amplitude is reducing. So in this near R equal to 1 or omega equal to omega n, we have only method to control the vibration is the we can induce the some damping. Now come to the phase angle. Phase angle we have already written here, phase angle. So phi equal to tan inverse 2 zeta r upon 1 minus r square. And we see here that we can plot the phase angle similar to the frequency response curve, as it is also function of zeta and r. So for r, and we have plotted phase angle. So what we can see that phase angle is it is 0, about 0 at low frequency, low r. Okay, so it start from 0. When r equal to 0, it start from 0, and it is increasing and going towards 180 degree when we are changing the r. Moreover, we see that all the curves are passing through phi equal to 90 degree at r equal to 1. So at resonance condition, for any value of damping, we have the 90 degree phase angle, that is fixed 90 degree phase angle, and this is independent of damping. For any damping curve, for any value of damping, all the curves pass through this phi equal to 90 degree. So if we have lower value of damping in the phase angle plot, okay, there is more abrupt changes. So here we see that if we have zeta equal to 0.125, okay, so or zeta equal to 0, you see zeta equal to 0 is this line. So this line at 1 it is going to 90 and then it is going to 180 degree. So very abrupt change of the phase angle. Similarly here zeta equal to 0.125, 0 to 90 and then 180 degree, towards 180 degree. So, at higher value of r they are tending to 180 degree, and lower values of r they are near 0 degree. And more abrupt the changes in phase angle about resonance, the more sharp is the peak in the frequency response curve. For example, zeta equal to 0.125, we have very abrupt change, we are 0 to changing to 180 degree, and here we can see zeta equal to 1 very abrupt peak. So, here in the frequency response curve, sharp peak. And for 0 damping, the phase lag suddenly changes from 0 to 180 degree at resonance. So, we discussed the magnification factor and frequency response curve. As frequency response curve are the function of damping. For different damping values, they give the response, steady state response, amplitude response at the range in the different frequency, force frequency. So, they gave us some information that can help us to design our system. I mean, we can select that what is our frequency range, and based on that what the response we want, we can select the damping value. Okay. So, these frequency response curve and phase angle plot, they give us very important information, and that is useful for about the single degree of freedom systems. So, thank you for your attention, and see you in the next lecture.